According to the Living Planet report of 2024, monitored populations have fallen by 73% since the 1970s. This is not just an ecological crisis, it's an economic and human one. Roughly 62% of rural Africans depend directly on biodiversity for food, fuel, medicine, and income. Yet fewer than 1 in 5 African countries has a functional system to monitor and protect these resources. The species disappearing first are those hardest to study. Rare, nocturnal, or solitary animals that slip through the cracks of traditional monitoring. Rhinos, relentlessly poached, are losing genetic diversity and reshaping entire savanna ecosystems. Leopards, elusive and mostly nocturnal, vanish and ultimately leave prey patterns shifting and their ecosystems falling silent. When these species go, we don't just lose wildlife, we lose carbon sinks, pollinators, and the balance that sustains local economies. Tourism, which powers 8.5% of Africa's GDP and sustains 24 million jobs, collapses when these species disappear. During the COVID-19 pandemic, the health and tourism showed the danger. Rangers went unpaid, patrols stopped, and poaching surged. The cost of biodiversity loss is not measured only in species. It's measured in livelihoods, resilience, and the future stability of entire ecosystems. Conservation monitoring is vital, but it's expensive, intrusive, and unevenly distributed. Helicopter surveys cost hundreds of US dollars per square kilometer, while protected area security runs over $500 per square kilometer per year. Small private reserves spend thousands each month just to keep ranger patrols going, and even advanced tracking isn't perfect. Radio collars can chafe, restrict movement, and alter animal behavior. To overcome these challenges, conservationists have adopted non-intrusive, motion-activated camera traps that detect heat changes when animals pass by. Over the past few decades, these tools have revolutionized wildlife monitoring, capturing over 253 million images from roughly 78,000 cameras across 112 countries, including more than 83 million wildlife detections on platforms like Wildlife Insights. Yet the sheer volume of images far exceeds what experts can manually process. This has fueled the rise of global AI models, systems trained across diverse species and ecosystems to automate detection and classification. Examples include Megadetector, which identifies animals, humans, and vehicles; Amazon's Deep Fawn, optimized for tropical fauna; and SpeciesNet, designed for cross-continental biodiversity analysis. These global models are accelerating conservation at scale, helping turn raw images into actionable ecological insight. But they still require localization, validation, and integration into African contexts. The question remains, are these global models truly doing justice to Africa's most vulnerable, data-deficient, and endangered species across the detection platforms? Our innovation bridges the gap between global AI models and African conservation needs through a unified African-centric framework. We follow a two-step process. First, benchmarking models like SpeciesNet across African datasets to expose performance gaps for endangered and data-deficient species. And second, fine-tuning them using data-aware methods that integrate endangered species metadata, taxonomic links, and few-start learning to better represent rare species. Unlike existing systems, ours will report when there is uncertainty instead of guessing, to flag these cases for ranger review. The novelty lies in contextual integration, aligning machine learning metrics with conservation risk and embedding human oversight through ranger-verified uncertainty flags. The result is a transparent, trustworthy AI pipeline that improves endangered species detection, reveals model blind spots, and strengthens collaboration between technology and local conservation experts. In short, it transforms camera trap AI systems from a generic classifier into an adaptive, human aligned decision support tool for Africa's most vulnerable species.
Yet, how realistic is this approach to actually solving the problem? To assess feasibility, we conducted a preliminary investigation into Google's SpeciesNet, one of the most widely used global wildlife classification models. SpeciesNet currently recognizes over 2,000 species categories and was trained on more than 65 million images. Its architecture combines megadetector for animal detection with EfficientNet for classification, assigning each image a species label and confidence score. When evaluated across multiple benchmark datasets, the model achieved a species-weighted F1 score of approximately 0.78 per species, demonstrating robust performance at a global scale. However, to determine how well this approach performs for endangered and data deficient species, we analyzed its underlying training data using information from the International Union for Conservation of Nature (IUCN), which classifies species into 9 red list categories ranging from least concern to critically endangered. We examined the global distribution of SpeciesNet's training samples. The findings revealed a strong geographic and taxonomic imbalance. The majority of images come from well-resourced Western regions and depict least concerned species. In contrast, data for endangered and critically endangered species, particularly across the African continent, are severely underrepresented. Additionally, training data had a long-tail distribution with threatened species like leopard and rhino with far fewer images. But what does this bias look like in the field? To test real-world performance, we evaluated SpeciesNet on an unseen dataset from Nkwatoka Reserve in Malawi. This dataset contained images of both least concerned species like the impala and endangered species like leopards, allowing us to assess how well the model generalizes to species of different conservation priorities. Because missed detections of endangered animals carry the highest ecological cost, we focused on recall as our primary metric. The results were damning. While the model recalled 68% of impalas, it only detected 18% of leopards, failing precisely where accurate monitoring matters most. We then sought to understand why the model struggled. Is it just data scarcity, or is there more to this? Using WildClip, a visual language model built on Clip, we generated image embeddings and tested textual hypotheses describing possible failure modes: a blurry photo, an animal at night, an animal partially hidden by leaves, among others. We applied HDB scan to group these embeddings and uncover consistent visual patterns. Two clusters stood out, one dominated by nighttime scenes and another where animals were partially obscured by vegetation. In other words, the model fails not only because endangered species are rare, but because the images are inherently harder, nocturnal, camouflaged, and behaviorally elusive. These findings confirm both the urgency and feasibility of our approach. To bring this project to life, we'll follow a clear, evidence-driven plan, one that builds on existing global models while directly addressing the blind spots for Africa's endangered species. Step 1 is baseline benchmarking. We start by testing Google's SpeciesNet as it is, the full pipeline with mega detector and efficient net, across more comprehensive African datasets, including Nkatoka in Malawi and data from Kenya Wildlife Service. This gives us a quantitative baseline for how well the model currently performs on endangered species recall and calibration. The main challenge here is data access, so we will aim to partner with conservation agencies to use anonymized, ethically approved datasets. Step 2 is data-aware fine-tuning. Here, we integrate the IUCN API so the system can fast classify whether a species is endangered or not, before refining with that smaller set. This boosts the model's attention to rare species, because endangered species are so underrepresented. We'll use data augmentation and taxonomic grouping to strengthen the signal. Step 3 is explainability and uncertainty. We'll apply generalized additive models to study how lighting, camouflage, and scene conditions affect predictions, and we'll quantify uncertainty at every stage, from detection to cropping to classification. If the model isn't confident, it will simply say unknown. Step 4 is bias and robustness testing. We'll use bootstrapping to simulate scarce data conditions and perform cross-reserve validation to make sure the system generalizes beyond the training sites. This step ensures the model isn't just accurate, it's stable, even under difficult field conditions. Across these stages, our approach stays realistic and grounded. We are not reinventing the wheel. We are adapting a working global model into an African-centered, uncertainty-aware conservation tool that's scientifically rigorous, ethically aligned, and ready for the field.
Ethics are embedded throughout our workflow, from data collection to model deployment. Camera traps routinely capture people, what's known as human bycatch, raising real privacy and consent concerns. To address this, all human images will be automatically blurred, clear signage will be displayed, and we'll follow free, prior, and informed consent protocols with local communities. We'll also restrict access to sensitive imagery and metadata, and obscure all geolocation data to reduce poaching risk. Our governance tackles dataset and geographic bias. Global models are often dominated by data from the global north, so we will prioritize African data sources and report performance transparently and by region. Finally, we aim to use uncertainty calibration to prevent overconfident errors for rare species, while routing uncertain cases to human experts for careful review. Ethical clearance will be obtained through partnering institutions and reserves, following international guidance on responsible camera trap use in conservation. Our team is small, diverse, and deeply connected to the African AI ecosystem. Austin Kaburia, a research intern from Nyeri, Kenya, leads our technical evaluation and model benchmarking. Taliya Weinstein, a biomedical and electrical engineer from South Africa, bridges data sensing and applied AI, ensuring the research remains rigorous and implementable. Kevin Kibaara, also from Kenya, specializes in digital media and software presentation, crafting the interface and visual communication that will make our insights accessible to non-technical audiences.
Our team blends scientific precision, engineering creativity, and design clarity, reflecting the Indaba's value of collaboration, inclusion, and African-led innovation. This project advances frontier AI for African biodiversity by building practical tools for rangers and policymakers while strengthening regional capacity through local partnerships. Thank you.